in some sense. So it will be a first approach to VRA0 to conformal field theory. And tomorrow I will show another approach to conformal field theory in this problem. So first, let me rederive. So I'm considering maps. So I have maps on a certain Riemann surface, and I have a certain number of marked faces and unmarked faces. So let me do that. So marked faces can do strange things, like this can be the same marked face wrapping around, and you can have and so on. You can have other marked faces. Sorry, so well, and so on. And so I remind you I defined two generating functions. So one was WNG, which was sum over t to the number of vertices, T3 to the number of triangles, T4 to the number of quadrangles, and so on. And divided by x1 to the length of the first marked face, L1. Let me use another color. So L1, L2, and so on. Xn to the Ln plus 1. Here, this is a sum over all maps of genus G and n marked faces. And in case I have no marked faces, so in case n equals 0, let me also put the number of automorphisms. Let me also consider another definition, which is more or less the same generating function, but with fixed lengths of marked faces. So T G of L1 Ln is, well, the same sum. So T to the number of vertices, T3 to the N3, well, TD to the ND, so possibly with automorphisms, but now maps with marked faces of lengths L1, Ln. So here this one is just sum over L1 Ln of T L1 Ln G over x1 L1 plus 1 xn Ln plus 1. And vice versa, if you know WNG, you can recover this one by picking the term with the given power of x1 in the denominator and the term with the given power of x2 in the denominator, and so on. So you can compute that by taking a residue, for instance. So let me remind you Tutt's equations, so which I wrote a little bit quickly the other day. So let me do it again, because that's what I will be using. So what happens when we want to erase the marked edge? So several situations can happen. On the other side of a marked edge, you can have a J-gon. So let's say this was marked face L1, and on the other side you get a J-gon. So what you get is a new face of size L1 plus J minus 2. Okay, and let's say instead of marking this edge, you will mark, let's say, the next one, so this one. Another possibility was that on the other side of the marked face, you have another marked face.
Maybe the edge should be in the opposite direction.
Sorry?
Yes, we used to have
The edge on the resulting map should be in the opposite direction, as I think.
No?
No? It should start from the... Not go into the...
we started on the past lecture one from the last vertex.
Maybe it doesn't matter.
No, it doesn't matter. Well, I mean, I don't remember which convention. Just you have to take one convention and always keep the same, but maybe it's not the same as yesterday. So now you have two. Well, okay. Let me say the marked edge here is this one. So you get now a marked face of psi L1 plus L2 minus 2. And the new marked edge will be, again, let's say. So the other day you say I used this one? Or this one? This one?
Yes.
You use this one, but in the opposite direction. The arrow was going into the...
No, I thought I was always using the convention that the marked face is on the right of the marked edge.
That's right.
Yes? So this is what we have.
Oh, so
Maybe it's because the other day I wrote the marked face on the exterior. Okay, that doesn't matter. So now we... Okay. So, but when we do that somehow, this is not bijective because so we don't have a 1-to-1 correspondence, we have a 1-to-L2 correspondence because if we want to go back, we have L2 ways to mark the other marked face. So we will have to be careful in when we count things. Excuse me?
The same face mark.
Here? Well, it's just in case the marking of that face was also on the same edge, since you remove the edge, you would have to consider a special case. So, I mean, you could do that, but it doesn't matter. But in any case, somehow you forget one of the two markings. Another possibility was on the other side of the marked face. So that's the case where you wrap around so when you wrap around, you will transform that into well, okay. So now you will mark the face. So just let's say the one before and the one after. That's where the marked edge was. Okay, and two situations can occur. So either you had something like that, and you get something like that, or you had a handle so what's where your marked face is. You get now something which will look okay. Okay. So here you see that you had genus G and n marked faces, and you end up with genus. You end up with, let's say, genus H and G minus H, and let's say n prime and n minus n prime. No, sorry. So let's not count this this one, n minus n prime minus 2. And here you started with gn, and you end up with g minus 1 and n plus 1. And here you had gn, you end up with gn, and here you have gn, and you end up with gn minus 1. There is one thing you can check, is that in this procedure, the Euler characteristics chi equals 2g minus 2, 2 minus 2g minus n. So the absolute value of chi is 2g minus 2 plus n. Because in general the Euler characteristics is negative in all those examples. So in absolute value, you can check that after doing this, after removing the edge, the Euler characteristics in absolute value decreases, or at least does not increase. Well, here it stays the same, but in all the other cases it decreases. So the absolute value of the Euler characteristic decreases. That's why this procedure leads to a recursion which ends after a finite number of steps. And it's called a topological recursion because it makes the absolute value of a Euler characteristic decrease. So how do we translate this into countings of maps? So let me write the other day I wrote the equation for WNG, and it's not so easy, but if we write it in terms of these, it's much easier. So let me write it this way: L1, L2, Ln, G. So somehow this is the left-hand side before erasing the marked edge. And since we have a bijective procedure, well, not really bijective, here we have multiplicity to take into account, but we know the factor of this multiplicity, it's exactly L2. So we have a bijective procedure, so the number of maps on the left-hand side should be the same as the number of maps in the right-hand side. So here we have sum over j equals 3 to d of tj t to the L1 plus j minus 2, L2, and so on, Ln, sorry, plus, so this case, sum from I equals 2 to n, so Li t to the, so, sorry, there is a g, and so here we have n minus 1 faces now. So we have somehow erased the face number I in this list, and we have replaced it by a face of length L1 plus Li minus 2. So let's say L2 and so on. And instead of Li, I replace it by Li plus L1 minus 2, and so on, Ln. The others are unchanged. And this Li is because we have Li ways to mark the edge. So plus, so let's see this term, t g minus 1, sorry, plus sum. Yes, and here the length of it, well, we had a total length L for the, so the total number of edges here on those two faces must be L minus 2, because we have removed, so we have removed somehow 1 and 2. So we must have L minus 2. So let's say this has length L prime and L minus L prime minus 2. So we have a sum over L prime equals 0 to L minus 2 of T L prime L minus L prime minus 2 L2 Ln. And here we will have sum from H equals 0 to G. No, sorry, let me write this first. Sum from L prime equals 0 to L minus 2. sum from H equals 0 to G, sum over all possible subsets L2, Ln of T, H, L prime I, and T, G minus H, L minus L prime minus 2, I bar. So we have to split this, this set into two complementary subsets.
L is L1.
Excuse me?
L is L1. Yes.
N? So L is L1. L is L1. Yeah. L is L1. Okay. So this is our recursion equation. So let me write it in case n equals 1. So when n equals 1, for instance, this term will be absent because there is no other face. So let me say T L G equals sum from J equals 3 to D Tj TL plus J minus 2 G plus sum from L prime equals 0 to L minus 2 Tg minus 1 L prime L minus L prime minus 2 plus sum from H equals 0 to G sum from L prime equals 0 to L minus 2 of T L prime H T L minus L prime minus 2 G minus H. Because the set L2 Ln is empty, so there is only one way to split it into two parts. Right? So this is the equation. Now there is, to see that we have a Varezor algebra somewhere, we'll need to define some operators, and those operators are acting by taking derivatives with respect to the TKs, to the TJs. So just observe one thing. Imagine that you are counting all maps, so like this, and take derivative with respect to tk here. You will have, so when you take a derivative with respect to tk, you will have nk coming out. So d over dtk of t L1 lng, what is it? So it will be sum of all maps. So t to the number of vertices, t3 and 3, and so on, td and d. But here we have tk will become to the power nk minus 1 and times nk. And also let me multiply by k. So somehow we get the generating function which counts also maps, but with one less k angle. And somehow it means that we have chosen, and there is a multiplicity nk. So, and there was precisely nk k angles. So we have chosen one of the unmarked k angles among nk, and we say that it's no more an unmarked k angle. And let's call it now marked k angle. So basically we have transformed an unmarked k angle into a marked k angle. And since a marked k angle should also have one marked edge, for a k angle there is exactly k possibilities to mark an edge, and this is exactly what this factor k is doing. So in fact this is the generating function of L1 Ln and k. So we have one more marked face. So one more marked face and length k. So taking a derivative with respect to tk marks a face. So now let's look at this equation again, and let's write it in terms of derivatives. So let me define, so notation will be that when there is no, so when n equals 0, I rewrite so what I call tg, so was also the same thing. So since there is no denominator, it's the same thing as w0g. And let me call that fg. It's the standard notation used by everyone for this object. So let me just call it fg. So what we see is that from the previous relation we see that d over dtk of fg is t kg. So one marked face of length k. So we had the 0 marked face, and now we get one marked face of length k. It's just a special case of this this relationship. And now k1 d over dt k1, k2 d over dt k2 of fg. Well, okay, let me write it. K1, K2, d2 over dt K1, dt K2 of Fg equals T K1, K2, G. So now we see that in this relationship, we shall replace the t's with only one marked face by simple derivatives of fg. And here we have a t with two marked faces. We shall replace it by a second derivative and see what we get. So take this relationship and just replace. So here we get, and also let me introduce the notation T2 equals -1. Okay, so that this term is just a special case of that. But now let me start with 2, and so I put this one on the other side and get 0. So because when j equals 2, this was precisely, this is minus TLG, which came from the left-hand side. Okay. So what we get is 0 equals sum over j of Tj L plus j minus 2 dfg over dt L plus j minus 2. Right, plus sum from L prime equals 0 to L minus 2, L prime, L minus L prime minus 2, dfg minus 1 over dt L prime dt L minus L prime minus 2, plus sum from L prime equals 0 to L minus 2, from h equals 0 to g, L prime, L minus L prime minus 2, dfh over dt L prime, dfg minus h over dt L minus L prime minus 2. Well, let me somehow sum over g this relationship and define. So let me define f of nu equals sum over g, nu to the 2 minus 2g fg. So I'm going to take this equation, multiply by nu to the 2 minus 2g and sum over g. So what do we get? We get that 0 equals sum over j tj l plus j minus 2 df over dt l plus j minus 2 plus sum over L prime equals 0 to L minus 2, L prime, L minus L prime minus 2. So here, since we have, well, I multiply by 2 to the 2, nu to the 2 minus 2g, and let me write it this way, minus 1, minus 2. Okay.
Nu is just a variable.
Sorry, nu is just a formal parameter which I use to define this function, this series. So here we see that we have nu to the minus 2 times exactly what we need to make f. So let me erase that. It was a d2 f over dt l prime dt l minus l prime minus 2. And in fact here we have plus, and when we do the sum over h, we will have, well, in fact we exactly get df over dt l prime times df over dt l minus l prime minus 2. So let me erase that now. Right. Now we can do, so it's an equation which contains first derivative of f, second derivative of f, and the product of two first derivatives. It's like a little bit like a Riccati equation. And the idea is to transform it like to a Schrödinger equation to make it linear. So, and the idea is to write that the good variable is not f, but f equals log z. So now when we do that, we will see that in fact the quadratic term disappears and we have only a linear equation for z. I mean, it's just a simple change of variable. And the reason is that 1 over z d2z over dt I dtj is exactly d2f over dti dtj minus df over dti df over dtj. I mean, this is just computing the log, the derivative of a log, the second derivative of a log. It's just very elementary. So now if we, it's a plus. Sorry, it's a plus. Okay, so that this is the second derivative of z. So what we get is so let me define the following linear operator. Notes. So let me define the following linear operator V L equals, in fact it's not exactly the same as here. I will shift L by 1. It's more convenient for the notations, or maybe even by 2. Yes, let me shift L by 2. V L equals sum over J L plus J Tj d over dt L plus j plus nu to the minus 2 sum from L prime equals 1 to L minus 1 L prime, L minus L prime, d2, well, d over dt L prime, d over dt L minus L prime. Okay, so this is the operator which acts on Z. And so the theorem is that VL applied to Z equals 0 for L. And in fact, since I shifted the definition of L, I'm not starting with 0, but with -1. So somehow this equation now is just, so you see it was just a reformulation of the Tut's equation. And now what is interesting is let's compute the commutator of two such operators. So another theorem is that, and it's just, I won't do the computation here, you just do it. So you take the product of two such operators applied to a function minus the two same operators in the reverse order, and you get that. So VL prime commutator you compute, and this is proportional to some v, to another such to one of those operator. It's L minus L prime VL plus L prime. So you can just check that by doing the computation. And so it's VR0, so it's VR0. So it is.
Sorry, we have shifted to L by 2, yes?
Yes. Yes, because probably this one was valid only for L.
Shift L prime there.
Sorry?
In the VL operator, in the second sum, we sum L prime from 1 to L minus 1.
Oh yes, no, but it's just because when L prime equals L or L prime equals 0, you get 0.
Ah.
Okay, it's just so I mean, even here I could have changed the bounds. Okay. I mean, in fact, so the term with L prime equals 0, you can remove it, and the term with L prime equals L minus 2 also is vanishing. So we see that Z is annihilated by all the positive, all the positive plus also the -1 generators of the VR0 algebra. Well, the problem here is that we don't define the negative VLs, the Ls with negative L. And so, for instance, we cannot, it doesn't make sense at the moment to speak about central charge. So because we are not considering negative Ls. And in fact, so as I said, this is just a first approach of why all this has to do with conformal field theory. But in fact, for the moment, we cannot really speak about conformal field theory because we don't have the negative VLs. So we don't know what they are. Tomorrow, I will talk about taking the limits of large maps, and then we can redefine the VLs with negative L. And so in this limit, they can be defined, and in this limit, we have really a full VR0 algebra. So, okay, so so this is the first part of what I wanted to say today. One can continue to use those relationships to derive many things, but I will stop in that direction for the moment. So I just wanted to show that those relationships are satisfied by the generating functions of maps. So now let me continue to compute the generating functions of maps. Well, so last time I showed you how to compute. So from the Tut equation, I showed you how to compute the function which I called W10. So the one with only one marked face on planar, genus 0. So W10 was, as I wrote, so there was two formula, v prime of x over 2 minus square root of v prime of x to the square over 4 minus some polynomial p10 of x, and t, and t3, t4. Okay, and where v prime, remember that v prime of x is x minus sum over j of tj x j minus 1. And there was a good change of variable, so change of variable. So x was alpha plus gamma z plus 1 over z. And alpha and gamma are functions of t, t4, t3, t4, and so on. And in this, and so it was such that W10 was t over gamma z plus sum from j equals 2 to d minus 1 of uj z minus j, where uj determined by v prime of x was sum of uj zj plus z minus j, and u1 was t over gamma, and u0 was 0. And this also determines alpha and gamma. So, and now I just showed you that, well, so this is the generating functions for maps with one marked face. Now, what if we want to compute generating functions of maps with no marked face, planar? So this is what I call F0. So W00, which was also F0, must satisfy, as I wrote before, df0 over dtk. K df0 over dtk must be equal to tk0. And tk0, you remember, is the term, so it's the W10 and term 1 over x to the k plus 1. So it's the 1 over x to the k plus 1 term in W10. So you can also say that this is the residue of W10 times x to the k. And as I said, a residue is in fact an integral, so you should always write dx. The residue is computed in the large x expansion, so when x goes to infinity, it's a residue at infinity. And in fact, the residue of 1 over x at infinity is not 1, but it's minus 1. You can see it by changing x to 1 over x. Well, so in fact, to be precise, this is the actual result. So we know W10. We have it explicitly here. We can compute this residue explicitly. So we know the derivative of F0 with respect to tk. And now it remains to integrate. Okay. It's not that easy to do, but if I give you an expression for F0, you can compute the derivative to respect to tk and check that it matches. So I will give you the answer. So I will give you the answer for F0. F0 equals 1 half of some, well, let me take my notes. Excuse me. Sum over j of j vj to the square plus 40 minus 1 to the j v2j plus 3t square over 2 plus t square log gamma square over t, where Vj determined by V of x. So take the primitive of that, so which is x squared over 2 minus sum of tj over j x to the j equals 3 to d. Okay, V of x, you decompose it, you will write it in the z variable, and you write it as 2v0 plus sum of j, vj, zj plus z minus j. So, knowing v and knowing alpha and gamma, you compute the vj's, you put them in that formula that gives f0. And you can check by hand, for instance, take the case of quadrangulations, you will have a very explicit expression, take the derivative with respect to tk, and you can check that it matches with that. So, this is how you prove this formula. But the proof, the proof for the general case is rather technical. So I just state the result. Well, this f0 has a very deep geometric meaning in general. So somehow geometric meaning. So w10 of x defines, so let's plot w10 of x as a function of x. Well, it will typically have well, it's not it's a multi-valued function because of the square roots. It's a two-valued function, in fact, here. Well, you can do the same sort of things for more complicated maps, like maps carrying an Ising model. And in general, when you have maps carrying an Ising model, you will get a multi-valued function with not a square root, but typically a cubic root or things like that. I mean, it will be a solution of a higher algebraic equation, higher degree algebraic equation, and there will be more branches. So it means that for a given x, there is not two branches, but it can be more branches. But what I'm going to say is valid in all cases. So here, I plotted x real, and I plotted, you see, for some values of x, there is no real value of w10 because of a square root. Sometimes what is inside the square root can be negative, and so you have no real value. So here I plot this function in r cross r, but in fact, you should not think it of, why should x be considered real? There is no reason. And in fact, what you want to consider is that x really should be complex, and then the value of w10 should be complex. So in fact, you should plot this in C cross C. C cross C, it's four-dimensional. It's difficult to make a plot on the blackboard. What you can say is that, so w10 is an analytical function of x. So it means that, or let's say you have an algebraic relationship between two complex variables, and a relationship between two complex variables means two relationships between four real variables. So you have two relationships between four real variables. So in a four-dimensional space C cross C, what you get is a dimension 2 manifold. So in C cross C, in fact, what you get is a surface. So, I mean, so in fact, this is called the complex curve, which is in fact a Riemann surface. So we should plot it as doing something like that. Well, in C cross C, this is really a surface. Okay, it's very difficult to plot, of course. I mean, you can take different sections, like X in give an imaginary part to X and plot. I mean, but you should really think of it as a surface. And surfaces have some geometric invariant, and one of them is the prepotential. And it turns out that the prepotential of that surface is exactly F0. Or F0 is the prepotential of that surface. I will not enter the details of the definition, but this is a fact. So, but in fact, more or less, the definition of a prepotential is that the derivatives are given by integrals of the function W10. So it's more or less what we have here. The derivatives are integrals with W10. This is more or less the definition of a prepotential. So, I mean, this is kind of, I mean, this already implies that F0 is a prepotential. So, okay. So let me continue with the two-point function. Well, what I just want to show by saying that is that, so W10 defines a certain Riemann surface embedded into C cross C, and more or less all the generating functions of maps will be somehow some invariance, some geometric invariance of that Riemann surface. For instance, well, F1, which is the generating function of maps on a torus, so on a genus 1 surface, with no marked faces, F1 will be the log of the determinant of some Laplacian on that surface. But so I will not do that now. Now let me consider something else. I want to compute W20. So it means genus 0 and 2 marked faces. So typically it will be something like that. And okay. And so on. And let me call that the cylinder. Because if you think of the marked faces as holes, somehow you have something genus 0 with 2 holes, and this is a cylinder. One property of cylinders is that when you glue 2 cylinders by their boundaries, you just get another cylinder. So somehow the generating function of cylinders should be a kind of self-reproducing function. So you better get something which is self-reproducing, otherwise you did something wrong. And there is a natural self-reproducing function on the Riemann surface. And there is only one. It's called the fundamental 2 form of a second kind, and so that's what we are going to get. So again, a lot of geometry. The fundamental 2 form of a second kind. Sometimes it's also called the Bergman kernel. Okay. Or for instance, on a genus 1 surface, this would be the Weierstrass function. Okay. Okay, let me write the Tut's equation for W20. Well, remember the Tut equation? It was TL1, so let me write it TL L2, 0, was sum over j of tj t L plus j minus 2 L2, 0, plus L2 t 0 L plus L2 minus 2, and plus sum over L prime equals 0 to L minus 2 t L prime L2 t L minus L prime minus 2 plus, in fact, plus sum over, so there are two ways. So we had to split the singleton L2 as I plus I prime, I bar. So there are two possibilities. Either I is equal to L2 and I bar is empty, or the other possibility, I is empty and I bar is equal to L2. So we can say this is T L prime 0 T L minus L prime minus 2 L2. But of course, this term is equal to that term, so you can just put a factor of 2 here in front. Right? You can take this equation and multiply by 1 over x to the L plus 1 and x2 to the L2 plus 1 and sum over L1 and L2 and sum over L and L2. That will give an equation for W20. And let me write the equation for W20. Okay, no, I don't want to erase that for the moment. So the equation for W20 will be that v prime of x, W20 of x, x2 equals, so in the right hand side you see that here we have a product of something with 2 marked face times something with 1 marked face. So we'll have 2 W10 of x, W20 of x, x2. And this term will correspond to taking a derivative plus d over dx2 of W10 of x minus W10 of x2 over x minus x2. And this is almost everything except that, in fact, when you take this summation, you see that here, since we have this L plus j minus 2, if we really want to reproduce W20, we should start the sum at L equals minus j plus 2. But we are starting the sum with L equals 0. So sum from L equals 0 to infinity, and sum from L2 equals 0 to infinity. But here, if you really want this to produce a W20, you should start the sum at 2 minus j. So somehow, when you sum from 0 to infinity, L plus j minus 2 is sum from j minus 2 to infinity, so you miss some terms. So somehow you have to complete the sum. So somehow you don't really get all this, you get this minus a certain number of terms. And let me call them P20 of x, x2. Well, there is one way to see what this P20 of x, x2 is. It's simply, so somehow the terms you miss are those which correspond to positive powers of x. So the terms you miss by starting with, if you start the sum not at 0 in L, but at 2 So if you do that, so if you start with L equals 2 minus j, so it means that 1 over x to the L plus 1 is j minus 1, so it's a positive power of x. So the terms you should subtract are all those with a positive power of x. And indeed, in the right-hand side, W10 contains only negative powers of x, W20 contains only negative powers of x. This term also contains only negative powers of x. So the left-hand side should not contain positive powers of x. And v prime of x contains positive powers of x. And so it just means that this quantity, P20 and P20 of xx2 is just the positive part of W20 of xx2. Plus means positive part. So it means you expand into powers of x and keep only the positive terms, the terms with a positive power of x. All right, so we have an equation, and well, it's not an easy equation to solve, but I will give you the solution. So, theorem, W20 of x. So let me move to the z variable again. X of z1, x of z2. And let me multiply by x prime of z1, x prime of z2 is 1 over z1 minus z2 to the square. So very simple answer. Well, minus, sorry, this is not completely all. No, but the other term is in fact much simpler. X of z1 minus x of z2 to the square. And so this is, while considering the difficulty of solving this equation, this is a remarkably simple answer and very universal. Well, in fact, this term, the function x of z, you see it contains this alpha and gamma. It may look complicated, but in fact, this term plays absolutely no role. And somehow it's the trivial term. Remember that what you want to do in the end is to expand in powers of 1 over x. And this term has a trivial expansion in terms of 1 over x. See that I've multiplied by that. So if you want to expand W20, you should divide by this. And so the numerator is 1 here. And this term has a trivial expansion in powers of x. And that's why it plays no role. So all the content of that formula is really in that term. And that term, in the z variable, it's completely universal. And somehow z, what is z in geometrical term? You see that, remember that we had x of z equals alpha plus gamma z plus 1 over z. And that W10 in the z variable was a rational function of z. So you see, in the x variable, W10 is multivalued. It contains square roots. It's multivalued. But when you use the z variable, it becomes a rational function. So really a monovalued function, somehow the simplest possible type of analytical functions you can imagine, rational function. And so what this means is that somehow z is the good variable of the problem, or it's the uniformization variable. So this Riemann surface is uniformized by the variable z. Z is the uniformization variable. So z, uniformization of this Riemann surface. So what this means is that you see that for a given value of x, if you want to find z, you indeed have two z's which corresponds to the same value of x. And somehow they correspond to the two z's which correspond to the same value of x are z and 1 over z. And they correspond to the square root. So changing z to 1 over z gives the same x, but gives, so somehow if this is z, this point is 1 over z. So we see that, well, somehow z is the good variable, and z lives in the complex plane, which means that this Riemann surface is, I mean, by this mapping, which is analytical, by an analytical mapping, this Riemann surface is in fact equivalent to the complex plane, or to the Riemann sphere, to P1. So, so Z is somehow the mapping of that surface into the sphere, Riemann sphere. So P1. And what is this function in P1? Well, this function has a double pole when the 2 points coincide. And it has coefficient 1 in the numerator. And somehow this is the unique rational function which has a double pole and no other pole. And it's called the fundamental two-form of second kind. And in fact, the fundamental two-form of the second kind is you multiply by z. You multiply by, it's a differential form. dz1, dz2, z1 minus z2 to the square. While here, it's really a tensor product of two differential forms. It's not the wedge product. I mean, it's not, it's a tensor product. But you see why we multiply by dz1, dz2 is that here we have this x prime, and somehow x prime, it's natural to multiply it by dz1 because then it becomes a dx. Well, x prime dx, x prime dz equals dx. So the fact that we have to multiply by x prime of z1 and x prime of z2, this quantity, to get something which is somehow universal, means that, in fact, when we change coordinates, this quantity changes like a two-form. Yes, it changes like a two-form. So this is, in fact, W20 is not really a function, it's really a two-form. And it should be multiplied by dx.
It's not exactly a two-form. At least there's a zero.
No, sorry, it's a multilinear, so it's a bidifferential somehow. It's the product of two, the tensor product of two differentials. Sorry, I call it a two-form, but it's a tensor product. So the theorem says that W20 of x1, x2, but times dx1, dx2 is, so this b of z1, z2, minus, so dx1, dx2 over x1 minus x2 to the square. But as I said, this term, in fact, will play no role when you start to do the large x expansion. So only this one plays a role. Let me give an example. So let's say you want to compute t, L1, L2, 0, so given length. So for that, you have to take residue when x1 goes to infinity, and residue when x2 goes to infinity of W20 of x1, x2, and x1 to the L1, x2 to the L2, and dx1, dx2. Well, you see, it's better to put the dx1, dx2 here, and x1 to the L1, x2 to the L2. Because you see now that, in fact, W20 will always appear with this with dx1, dx2. Whenever you want to compute some actual numbers, you will always multiply by dx1, dx2. So now, if we want to compute those residues with this term, in fact, you easily find that you get 0. Somehow, this term is just there to somehow to kill the pole at coinciding points, but it plays no role when you want to compute those numbers. So somehow it's just a regularization term, but it contains no information about the number of maps. So then it's good to change the variable. So it's also residue when z1 goes to infinity, residue when z2 goes to infinity, and now it's just dz1, dz2 over z1 minus z2 to the square. So x of z1 to the power L1, x of z2 to the power L2. Let me take the example of quadrangulations. Or let me just remember, so b equals dz1, dz2 over z1 minus z2 to the square. Let me say again that this is the fundamental form of the second kind on CP1, on P1, on the Riemann sphere. So this is the Riemann sphere, and it's also called the Barman kernel. So here in this example of counting maps, the curve which we have here, so the Riemann surface is equivalent to has the same topology as the Riemann sphere. So it's the Riemann sphere more or less. It's an embedding of the Riemann sphere into C cross C. But in other problems of counting maps, for instance, if you count maps which carry loops on them, you can do more or less the same computations, but in the end, this Riemann surface will have genus 1. It will be a torus. And then the fundamental two form of second kind, the fundamental form of the second kind on the torus is replaced by the Weierstrass function, so which is the only function on the torus having a double pole, no other pole. So this is the Weierstrass function. But this result, so the fact that the two-point function is the Barman kernel is a general result. It's valid for not only for just simple maps, it's valid for maps with an Ising model, it's valid for maps with an ON model, it's valid for many sorts of maps.
Wait, so we started with maps on the sphere, right?
Oh yeah, no, but the geometry of that function, so remember this Riemann surface is just the Riemann surface associated to the algebraic equation satisfied by W10. It has nothing to do with the maps we are counting.
But we counted maps on the sphere, really?
Well, yes, but...
Is it okay? So in high genus?
No. In all genus, so every WNG will be determined in terms of that Riemann surface. This Riemann surface is not the one on which you draw the maps. This is the Riemann surface which represents this function W10.
Yeah, but it depends on the genus also. Is it?
Sorry?
I mean, the surface...
This surface has a certain genus, but the genus of that surface has nothing to do with genus on which you count maps. This is not the same genus. This is, this is two different things. So, let me just do this computation in the case of quadrangulations, and I will finish.
This surface is always quasi-projective, yes?
Yes. At least for maps it is, but for the loop model maybe it is not. I'm not sure. Okay. Right. Okay. So So let me do quadrangulation. So in that case, x of z was gamma z plus 1 over z. And remember, gamma square equals 1 over 64, 1 minus square root of 1 minus 12t t4. So now we want to compute t L1, L2, 0. Just compute this formula. But it's easy to see that you will get 0 until L1 plus L2 is even. So in fact, let me choose directly L1 plus L2. So let me choose directly L1 plus L2 equals even. Well, we will see in the computation. So we just get residue of one z1 and residue in z2 of so dz1, dz2. Let's expand that as a power series at large z1. So sum over k of k z2 to the k minus 1 over z1 to the k plus 1. So I'm first computing the residue in z1 and then the residue in z2. So x of z1, so here it will be gamma to the power L1 times this quantity. So let's put the gamma L1 and gamma L2 in factor. And here we'll have z1 plus 1 over z1 to the power L1. So which will be sum over, let's say, m of L1 m z to the L1 minus 2m. Sum over, let's call it m prime of L2 m prime z prime to the L2 minus 2m prime. So we want to pick the term in z1. Sorry, it was z1 and z2. We want to pick the coefficient of z1 to the minus z1 of 1 over z1 in this formula. So it means that we want to have k equals L1 minus 2m. So so this is equal to gamma L1 plus L2. So we have already done the residue in Z1. And so we are left with the residue in Z2. So we have k equals L1 minus 2m. We had the sum over m and m prime. L1 minus 2m. So L1 m. And we are left now with and L2 m prime. And we have Z2 to the power, so L1 minus 2m minus 1 plus L2 minus 2m prime. Right? We had the constraint that k must be positive because the sum was over k equals 0 to infinity. So now we know that m should be smaller than L1 over 2. And now we want to compute the term in Z2 to the minus 1. So this means that L1 plus L2 must be equals to 2m plus m prime. So we see that L1 plus L2 better be even. Otherwise we'd get 0. Okay, so this is so. So this is gamma L1 plus L2. So sum over, let's say m, which is smaller than L1 over 2. So L1 minus 2m, L1m, and L2. And so m prime is L1 plus L2 over 2 minus m. Okay. And so this is the formula. So this was our T, L1, L2, 0. this quantity is a universal number which depends only on L1 and L2. It's just a pure number. It's an integer number. And it's really a pure number. So it means that all the dependence, well, all the non-trivial dependence is in this. So this is completely universal. So the number of cylinders is really a universal function. And now if you replace gamma by its value, you expand into powers of T4, you really get the number of quadrangulations, of cylinder quadrangulations. You really get the numbers completely explicitly. So this was just, so I will stop here. So it's just to show that you can really use those results to really compute things explicitly. So, okay. Tomorrow I will try to talk about the large size limit of, the limit of large maps. So with a very large number of faces. And see again integrability. Okay, thank you.